allow me to draw the dielectric slab again. So here it is, and its properties are it has a thickness T, like that, and it has an index N. And we'll assume we're in air and that the index outside is 1. So if we have a plane wave come in with irradiance I naught, and it comes in at some angle to the normal, theta I, we know that it's going to, part of it is going to reflect at the same angle, but part of it is also going to come down and then reflect off the back, and it'll emerge actually at the same angle as the front reflection. So we could also define that for later as theta t, the refracted angle. And we could think about these two reflections. The first one we can call I1. And we talked about how it's basically 4% of the incident irradiance. If you have n equals 1 here and n equals 1.5 here, you get about 0.04. So I1 is about 0.04 I naught. And then we also thought about how this one actually is pretty close to 0.04 I naught. So it's a little bit different because you lose a little bit there. This is about 4%. So I2 we approximate as 0.04 I naught. And the reason we do that is it gives them the same value and it makes the interference calculation a little simpler, although only an approximation. But everything's only an approximation anyway. Let's see, so that's all we need. So now let's figure out what we're trying to do. What we're trying to do is to calculate the irradiance that's reflected, IR. All right? Well, this is just the superposition of two plane waves. So we say IR is, let's see, it was I1 plus I2 plus the cross term cosine delta. So in this case, I1 and I2 are the same. It's 2 times 0.04 I naught. Okay? And then the cross term, remember, is a factor of 2 in the intensity. So that's also 2.04 I naught cosine delta, the phase factor. And then remember that sometimes some books will use a trig identity to write this as 4, in this case 0.04 I naught cosine squared delta. So either way you want to get it to go from 0 to 1. Either way. Okay, so next we got to figure out what is the phase factor for this situation. So before we got the phase factor YDS, Young's double slit. Now we're getting the phase factor for TF, thin films. Okay? And remember, it's 2 pi times these deltas. 1 is for the path, and 1 is for the phase. So remember, we like to write it in terms of a distance, just traditionally, over the vacuum wavelength, lambda naught. So here's the second problem where we got to think about those deltas and really sort of define them. Okay? So let's first think about them. Let's start without one of the deltas. Let's talk about the physical path difference between 1 and 2. Well, this one goes off and this one reflects down and back up. It's clearly related to traversing the film twice. And now I forgot one thing I meant to write. We're doing this for theta I approximately equal to 0. So we're just doing this for very close to normal incidence. That's what makes these 4%. And that's also what makes the physical path difference 2t. Right? The physical path difference is 2t, twice the thickness. This beam reflects right away. This beam has to go down 1t and back up 2t. But that's not quite delta path, right? Delta path equals the optical path difference. So since what these are really keeping up with is the number of cycles you go through, because it's an interference phenomenon, well, the number of cycles you go through actually depends on the index, because the index effectively changes the wavelength. So how many cycles you go through per unit distance. So all you got to do is multiply by n. So it's 2tn for normal incidence. Okay. So that's that one. And then there's the reflection right? The delta phase. So what could cause changes in phase? What could it possibly be? Well, in this case, it could be reflections. You're reflecting here, and you're reflecting here. So we'll call this the reflection path difference. The reflection phase path difference, because it's not really a distance that causes this. It's really just a phase shift, but we give it in terms of a difference. And usually, you just kind of have to think about what it is. So if we look at it, we know that on an external reflection, this will have a pi/2 phase shift. Okay? Now you could say, what about TE and TM? Well, actually, when you go at normal incidence, it's the same thing. Now you say, no, wait a minute. Little r was positive for TE and negative for TM, so it depends on TE and TM. It actually doesn't. So I didn't go through this back in LS3 because we were pretty busy. But if you looked at the fact that little r was positive for one and negative for the other, but then you thought about the field vectors and brought them to normal incidence, you see the way we drew one, we assumed no phase shift, and that would give us negative little r. And the way we drew the other actually assumed a phase shift, and that gave us positive little r. So actually it all works out. You do get a phase shift near normal incidence, whether you think of it as TE or TM. It actually doesn't matter whether you call it TE or TM because the plane of incidence is not well defined when you come straight down. All that, I'm saying all that to tell you there is a pi phase shift right there. Okay. You could also see it by just doing a quick evaluation of little r. It's 1 minus n over 1 plus n, and if you plug in 1.5, you get negative 0.2, right? Here. What about here? Here you actually get no phase shift. Okay, you don't even have to believe me. We can do it real quick. R is 1 minus the index, but now since we're at an internal reflection from high to low, it's 1 minus 1 over n over 1 plus 1 over n. Now multiply by n over n, and you get n minus 1 over n plus 1. And there you go. You get 0.2, but it's positive, so you don't get a phase shift there. So there's a quick check for normal incidence, a lot quicker than going through the full Fresnel equations at an angle. Anyway, pi/2 phase shift here, no phase shift here. The phase difference is pi/2. But if you want to express pi/2 as a wavelength, then you call it 1/2 lambda naught. You express it in terms of the vacuum wavelength. You don't think about what material you're in because you're really not thinking about a propagation through a material. You're just thinking about the instantaneous difference in phase. So those are the factors. So now we will use those and see what happens.